we are with those kind of problems. Very good. Was there any other problem or issue you want me to go over? Please let me know. Did you get this, guys? I think this was one of your homework assignment on this Pearson site, and from section 1.3 when they talk about slope field. So although this is not slope field, but it's a consequence of that section, which is how to graph solution curves for autonomous equations without solving. Notice the question was do not solve. Even though we could solve, but the idea was do not solve. Just for inspection, draw some solution curves and tell us whether the system is stable, unstable, or half stable, half unstable. Yes? So if you have, let's say, 16, and the curves go like this, so this would be unstable, correct? On the other hand, if you had the equilibrium point at 16, and right here, they would get close to 16, but up here, they would go away from 16. This is called what? Half stable. Half stable, okay? So it's neither stable nor unstable, it's half, okay? Sometimes these are considered to be stable depending on the situation in real life. So we don't throw these out. But the ones which we don't care is these guys, unstable. Rain or shine, they are not going to work. The system is going to go through a chaotic what? Changes, and it's never going to what? Settle to the equilibrium position. So these are very unstable. So the system is not going to function permanently. So right away, the minute you turn on the switch, the system is going to break down. So that's basically what we have. So we good? All right. So last time we talked about, let me just bring you up to speed, then I can show you more examples. These were called 4.2, which was called homogeneous equation of second order. Although you can extend this to higher order, but let's just start with second order, okay? Everything we did in chapter 1 was based on first order. Anyways, so basically this is how the equations are going to look like. A y double prime plus by prime plus cy equals 0. These kind of equations are called second order, linear, homogeneous, because you got a 0, equation with constant coefficients. In other words, A, B, C are no longer functions of x, they are constant. If that's the case, then what? You will always have two solutions, right? And those solutions are called fundamental solutions, provided they satisfy three conditions. What were those conditions? The solutions, what? Should satisfy the equation, all right? The solutions should be linearly independent. What's linearly independent? That means if you take the ratio of two solutions, it should not be a constant. In other words, they should not be combinable, yes? Also, the number of solutions you come up in fundamental solutions should match the order of differential equation. So if the differential equation is second order, you gotta have two of these. If it's third order, you gotta have three of these, and so on and so forth, correct? The next thing we learned was the form of the solution, which was what? Kind of like this. This is the form of the solutions for these kind of equations. You know, linear, higher order, homogeneous equation with constant coefficient. The solutions, rain or shine, is going to look like this. It's going to be an exponential function, e to the power of rx, where r is any real number. Okay? So last time I did a couple of examples. And luckily, the roots of this so-called auxiliary polynomial came up to be distinct real. Tonight, we would like to see what happens if the roots come up repeated or even complex, meaning it has a imaginary number I in it. Then how would the solution look like for these kind of equations? Once again, let me just bring you up to speed. If the solutions are going to be in this format, so if you plug that in, take what? Two derivatives and plug those into the equation, lo and behold, that's going to create this polynomial. So that's a polynomial which has a name. It's called auxiliary polynomial. The roots of that polynomial will tell you what R is. So in this case, notice there is absolutely no need to go through these steps. By inspection, look at the differential equation and write the auxiliary polynomial. Replace what? This guy with, pretend you are substituting y double prime with r squared, y prime with r, and y with 1. So this equation, the auxiliary polynomial for this differential equation looks like r squared minus r minus 6. You can factor it, so you get 3 and negative 2 for the roots of this auxiliary polynomial. Therefore, the fundamental solutions, so these are called fundamental solutions, are e to the power of 3x and e to the power of negative 2x. However, that's not enough. Now we can take the linear combination of these guys. That means we multiply this guy by some scalar, multiply this guy by a different scalar, add them up, and this is also the solution of that differential equation. And what you have inside the box is called general solution. Do you all see it? Question is, and if they give you what? Initial conditions. So these are called initial conditions. These guys are called IC, initial conditions. Then you need to find what? The constants. Once you find the solution, which is inside the box, then impose the conditions. Like y of 0 is 1, y prime of 0 is negative 1. So impose the condition on the solution itself and its derivative. That would give you two equations, two unknowns in terms of C1, C2. Solve, you will get these two numbers. C1 is 1/5, C2 is 4/5. Go back and replace the C's with those constant. So this is called particular solution. Notice particular solution has no C in it because it's a specific solution. It has to also go through this point and satisfy this derivative. Do you see it? So not always the function is what? Well, what should I call this? Factorable. For instance, let's say you were asked to solve, let's say y double prime to minus, let's say, oh God, 3y prime, okay, minus, let's say, 7y is equal to 0. Okay, so can someone tell me, please, by inspection, what would be my auxiliary polynomial equal to, please? Anyone? Shout it out if you know.
R squared minus
R
3R
squared
7
minus
3R
3R minus
minus 7 equals 0.
equals 0. Solve for R. Thank you, sir. Solve for R. Sometimes, you know, the equation is not factorable. That's okay. That's why, because it's quadratic equation, so we use quadratic formula, correct? So I would say this is equal to R is equal to, what is it, negative B plus or minus square root of negative B squared minus 4A C over 2A. Remember, A is equal to 1, B is equal to negative 3, and C is equal to negative 7. quadratic formula from algebra 1. So r is equal to what? 3 plus or minus 9, 28, 2. That's 3 plus or minus, what is it, 37 over 2. So therefore, r is equal to 3 minus square root of 37, is that right, over 2, or r is equal to 3 plus square root of 37 over 2. Therefore, the fundamental solutions, they're going to look ugly, but that's okay. There it is, that's one of them. Here's the other one. You all see it. But that's not good enough. That's not it. That's not the solution. That's just fundamental solutions. But the final answer is a linear combination of these guys. So I got to go C1, e to the power of 3 minus square root of 37x over 2, plus C2, what? E to the power of 3 plus square root of 37 over 2x. Now this, ladies and gentlemen, is the final answer. And if they give you initial conditions, then you can find the C1 and C2. Okay, couple of things to note. Because the order was 2, so I came up with 2 C's. Also, I came up with 2 fundamental solutions. Do you all see it? So the question is, what if, what? The order was higher than 2. How would you handle those guys? Well, similar to what we did for this case, except now instead of quadratic equation, you will end up with what? Third degree equation. For instance, let's take a look at this problem, if you don't mind. So this is okay, right, guys? So sometimes, you know, the roots may not look nice. Also, notice what we have under the radical is b squared minus 4ac, which is called discriminant. Discriminant, in our case, was what? Was positive, because it came up to positive 37. So there are 3 scenarios. So there are 3 cases, case 1, case 2, and case 3. If the discriminant is positive, expect 2 distinct, that means different, real roots. Notice these are distinct, they don't look alike, but they are real numbers. However, if b squared minus 4ac is equal to 0, expect 2 what? Repeated real roots. So they're going to be repeated. Like in this case, you're going to get R1, R2. In this case, you're going to get R1 twice. In the last case, if b squared minus 4ac is less than 0, you know what's under the radical, let's say this guy came up to negative square root of 37, then we would have 2 complex roots. And they're going to be what? What is it called? Conjugate of each other, which means r is going to be a plus bi, or r is equal to a minus bi, where I is the square root of negative 1. So these are called pair of conjugate complex numbers. So complex roots, they always come in conjugate form. In other words, if one of them is a plus bi, you can bet your money the other one is a minus bi. We like to examine these 2 scenarios tonight. Well, before I do that, let me also show you one higher order differential equation so you guys can see we can what? Apply this concept to higher order. You don't have to stop at 2, okay? Did you all get all this? Yes? We good? So it all depends on the number under the radical. If it's positive, 2 distinct roots. 0, repeated. Less than 0, expect complex roots, you know. roots with I in it. However, the solution will never ever have I in it because the equations are based on real functions. So I'll show you how to bypass that. Suppose we have y triple prime plus y double prime minus 2y prime equals 0. Question is solved. Remember, solve means what? Find y of x such that it satisfies this equation. This equation is called third order linear homogeneous ODE with constant coefficients. That's the title of this equation. Excuse me. Because it's third order, expect 3 fundamental solutions. Expect 3 C's in your answer, correct? So expect, is that right? So by inspection, write the auxiliary polynomial. What is it? What is the auxiliary polynomial? Could someone tell us, please?
R cubed
R cubed
plus R
plus
squared
R squared
minus
minus 2R. Set it
equals
equal
0.
to 0, find R. So remember, there was no Y, so there is no constant. So this is Y, that's R squared, that's R cubed. Okay, because this is third degree, so I need 3 answers. How do I do that? Factor out an R. But this guy still factors. 2, 1 plus minus. Set each of these guys equal to 0, one at a time. Solve for R. One of your answer is 0. The other guy is -2. The last one is 1. 3 roots because it's a third degree auxiliary polynomial. So fundamental solutions, e to the 0x, e to the -2x, e to the 1x. But that's not it. The final answer is a linear combination of these guys. I gotta have C's in my answers. Remember, expect 3 C's. So you kind of go, what? C1 e to the 0x, C2 e to the -2x, C3 e to the x. But e to the 0x is 1, so that's C1 plus C2 e to the -2x, C3 e to the x. 3 C's. And there's no way I can combine the C's. Okay, there's no way. So, the question is, how in the world do you decide these are linearly independent? Unfortunately, what? Dividing these guys 2 at a time or something like this doesn't work. So what we have is called Wronskian, okay, which is shown by W, which will be function of F1, F2, F3, and they are functions of X. So in order to determine these 3 functions are linearly independent, remember, these are not just any functions, these are solutions. So here's what we do. Wronskian is a 3 by 3 determinant. I don't know if you had a experience with determinants. These are like matrices, and it's going to be square because I have 3 functions. So I'm going to have 3 rows and 3 columns. And this is called determinant, which is a real number associated with any square matrix. We're going to learn all about matrix in upcoming chapters in linear algebra part. But for now, here's what you do. You list the functions in the first row. Because it's what, 3 functions, you take the derivative of these guys and put the answer in the second row. And then you take one more derivative and put it in the what? Third row. Now you evaluate this. Those of you know how to evaluate this, more power to you. If not, stay tuned for linear algebra. I'll show you how to evaluate. So the question is this: if this guy doesn't come up to 0 for what? At least one value of x in the domain of what? F1, F2, and F3, then we say, aha, F1 and F2 and F3 are what? Linearly independent. So if you do the determinant and it comes up to 0, not equal to 0, for at least one value of x in the domain of all these three functions, F1, F2, F3, then they're linearly independent. But can I say if it comes up to 0, they are linearly dependent? No. If there are solutions, you may, yes. If you know these are solutions to a differential equation, if it comes up to 0, you can tell they're linearly dependent. But if these functions drop from blue sky, there are some random functions. If this guy comes up to 0, the test fails. So now we have to attempt to examine the dependency via some other methods. But if these functions, you know they are solutions, then if this determinant is not equal to 0 for at least one value of x in the domain of these three functions, they are independent. If it comes up equal to 0, they are dependent, provided these guys, you know, they are solutions of some sort of differential equation. Do you see it? So now the idea is, let's go back to this problem. Let's say the question is now y double prime of x plus 4y prime plus 4y is equal to 0. Once again, solve. Mayday, mayday, we have a problem. What's the problem? Problem is, what is my auxiliary polynomial? Is it r squared plus 4r? I have a y here, so this guy doesn't take r, it's just 4. Set it equal to 0, factor this, okay, you get this guy twice, right? And then if you set these guys equal to 0, you get real roots, but repeated. Repeated real roots. Mayday, mayday, we have a problem. What's the problem? Problem is, what would be my fundamental solutions? One of them I know it's e to the negative 2x. What's the other one?
You can't have another one.
Well, if you say the other one is also e to the negative 2x, that's wrong. Why? Because these guys are linearly dependent. They are combinable. How do you know that? Because I have two functions, I don't need to use Wronskian. I just what? Do the ratio. And guess what? It's 1. It's constant. So they are linearly what? Dependent. So I cannot claim, so this is not a fundamental solution. So I can go C1 plus this, C2 plus that. So let me see if we have any comments here. Yeah, okay. Shamima, let me catch up with you. Okay, so so if you say linear combination of these guys, check this out. You're supposed to write C1 e to the negative 2x plus C2 e to the negative 2x. Remember, we were supposed to have two C's, but this ain't two C's. Why? Because I can always factor out what? E to the negative 2x and call this C. So guess what? I only have one C. And that contradicts our rule, because our rule says, depending on the order of differential equation, You got to have that many C's. So therefore, this doesn't cut it. Okay, so one of the solution is e to the negative 2x, but the other one is not identical to the previous one. Turns out the claim is what? If you have repeated roots and the first one is this, the second one is x times e to the negative 2x. So there is a factor of x. This is like if you have two repeated real roots. Okay, so so what? So so what if, so before I show you where this x is coming from, let me impose a question. What if I solve this polynomial and set it equal to 0? I got negative 2 what? We call that multiplicity 3. So here we call this multiplicity 2, which means you have two repeated roots. But suppose you solve the equation, you got this 3 times, which we call that multiplicity 3. What if your auxiliary polynomial gives you 3 of these? So how would the fundamental solution look like? Do you want to take a wild guess? Anyone? So for 2, multiplicity 2, that means 2 repeated. One of them is e to the negative 2x. The other one is x times e to the negative 2x. What if I got 3 of them which look alike? Let me see. What is this? Yes. So it will be e to the negative 2x, x e to the negative 2x, x squared e to the negative 2x. There you have it. Okay, do you see it? So let's generalize the formula, shall we? So suppose what? Here is a general formula. General formula. Suppose I set auxiliary polynomial and R came up to R1 with multiplicity what? M. Let's say these guys, this root, I came up with m many of this root, same root, m many times, m many times. So what would be the fundamental solution? The first one is e to the r1x. What's the second one? X times e to the r1x, x squared e to the r1x. What will be the last one, guys? X to the power of what? What will be the last one? Let me see.
To the power of m.
Sorry?
To the power of m.
M minus 1. Not m. Why? You remember when you have 2 repeated roots, you stopped at x to the first. When you have 3 repeated roots, you stopped at what? X squared. So this has to be m minus 1. You know why, don't you? Because the first one right here is x to the 0. So you go 0, 1, all the way to m minus 1, not m. Okay? Can you see it? Notice multiplicity 3 stopped at 2. Multiplicity 2 stopped at 1. So the degree of the last x factor is 1 less than your multiplicities. So it must be m minus 1. Do you all see it? So go back to the problem. So none of these are solutions. So the fundamental solution is e to the negative 2x, x times e to the negative 2x. So the general solution is C1 e to the negative 2x plus C2 x e to the negative 2x. Ladies and gentlemen, my final answer. Do we all see it? Okay. M minus 1. Correct, Pedro. M minus 1. Did I move that fast? Where did it go? Right here. M minus 1, provided what? Multiplicity is M. Let's say M was 4. So fundamental solution would be e to the r1x, e to the rx times e to the r1x, x squared e to the r1x, and then the last one will be x cubed e to the r1x. Notice it's always 1 less than the multiplicity. Do you see it? So it's m minus 1. That's where you stop. Question, where these x's coming from? Why do I have x? Okay, that's a good question. Here is why. Notice if one of the solutions is e to the x, the other one is not e to the x. The other one is what? X times e to the x. Why is that? Well, remember, if I want to find what? If I want to, well, if the solutions are going to be linearly independent, so the ratio of what? There's two solutions I'm going to come up with. Let's say I have a second order linear homogeneous differential equation with constant coefficient. So it cannot be a constant, so it has to be a function of x. Why? Because this is what it takes for the functions to be what? Linearly independent, meaning you cannot combine them. Well, if that's the case, then what? My unknown function y2, remember my first function is e to the x. I want to know where do you get this guy from, x times e to the x? Where does x is coming from? Okay, so this is like my y1, this is like my y2, but I'm not sure where this guy is coming from. So here's why. Take the ratio, set it equal to a function of x because they're supposed to be linearly independent. Solve the equation for y2. Take what? Two derivatives of this guy. Remember, this guy is a function of x, that guy is function of x, so we got to use what? Product rule. Take two derivatives, call these equation 2, right? And then go back to the what? Original equation, this guy, right here. That was the original equation. Notice the auxiliary polynomial came up to r minus 1 equals 0. So r is equal to 0 with multiplicity 2. So I'm going to show multiplicity for, just to make sure I don't have to write the whole thing over and over, with m-2. Okay, so I'm going to take 2 and substitute in equation number 1. So substitute 2 into the original equation 1. When you do, some of this stuff cancels and you get this equation, u double prime is equal to 0. But if you what kind of what take antiderivative of both sides, what would you end up with? You will end up with what? U prime is equal to C1. How is that? Take the antiderivative of both sides, of course, with respect to x, correct? So you get u prime of x is equal to some constant. So there it is, okay? But now take the derivative, antiderivative of u prime of x equals C1 one more time to get u. So in this case, you get u of x is equal to C1x plus C2. Okay, so this is a linear equation, isn't it? What would be the simplest linear equation you can get your hands on? What should C1, C2 to be equal to for this to be still a linear equation? Any guesses? I want the most simplified form of this linear equation. You know what linear equation is? It looks like this, mx plus b, remember from algebra classes? What would be the most simplified form of this equation? What should m and b equal to? Pretend this is m, pretend this is b. Any idea? What should I replace C1, C2, and yet still have a what? A linear equation. Because I don't want to lose the linearity of the equation. I can afford to lose the x, then it will be a constant. Okay.
C1 has 1 and
Oh.
C2 has 0.
Very good. So excellent. Replace the m with 1 and this guy with 0. As the gentleman mentioned, replace this guy with 1 and this guy with 0, and you will end up with u is equal to u of x is equal to x. This is the most what? Simplified linear equation. There. But wait a minute. What was y2 equal to? y2 was e to the x times u of x. What did we come up with for u of x? X. So y2 is e to the what? X times x. That's where x is coming from. You can also find y3 based on y2 going through the same procedure. So it's not magic. It's just like we have to maintain the independency of the function. In other words, I cannot have e to the x and e to the x twice and claim that's a fundamental solution, because that violates the independency. So I have to take a ratio, set it equal to a function of x, not constant, and somehow what? Solve that equation for u, and turns out u is equal to x, which is the most simplified form of a linear equation, correct? Incidentally, I was going to say, right, so that's basically what that is. So do you all see where this guy is coming from then? So we're good, right? You all see it. So, right. So are we okay? So shall we do a problem just to make sure we're all on the same page? How about this guy? Z double prime, suppose these are functions of x, okay, minus 2z prime minus 2z is equal to 0, and you have two initial conditions, namely z of 0 is 0, z prime of 0 is 3. So auxiliary, first of all, when they say solve, what am I solving for? Any idea? Remember, the idea is solve. What does that mean? What am I finding? Anyone? What am I solving for?
What z equals?
Yes, I'm solving for z. You always, rain or shine, remember this is second derivative of z with respect to x. This is like what? First derivative of z with respect to x. This is like the function itself. So you always solve for the dependent variable, which is z, correct? Let me see what we got in the chat. Yes, z. And if this guy was function of t, then they should have what? Let me know ahead of time. If they don't, I take it as function of x. Anyways, what's my auxiliary polynomial? R squared minus 2r minus 2. Is that right? Is that factorable? I don't think so, is it? So I'm going to use quadratic formula, which is 2 plus or minus 4 plus what? 8 over 2. Is that right? That's minus b plus or minus b squared minus 4ac. So this would be like what? 2 plus or minus square root of 12 over 2, which is 2 plus or minus 12 is 4 times 3, so that's 2 square root of 3 over 2. But then you can divide top and bottom of this fraction by 2, get plus or minus square root of 3. So we got real roots. That was not the intention of this problem, but hey, it's a done deal. Let's finish it. So fundamental solutions, e to the power of 1 minus square root of 3x and e to the power of 1 plus square root of 3x. But you and I, we both know that's not the answer. The answer is a linear combination of these, c1 e to the 1 minus square root of 3x, c2 e to the power of 1 plus square root of 3x. Okay? I think the purpose of this, I brought it up so you can see how am I going to find the c's, because the minute you have initial condition, so when they say solve, that means find a particular solution, not general solution. Why? Because look what's next to the problem, initial conditions. Okay, sorry guys.
Y and Z.
Yeah, I just noticed. Thank you so much. Appreciate. Thank you. That's what we have this whiteout. I didn't practice what I preach. So yes, this is Z. So impose the first condition, 0, and replace the what? X's with 0, so you get this. Okay. To impose the second condition, I have to take a derivative of my answer, which is z prime equals 1 minus the square root of 3, c1 e to the power of 1 minus square root of 3x. And this guy is 1 plus the square root of 3, c2 e to the 1 plus square root of 3x. Now impose this condition. What does that say? That says z prime is 3 when x's are 0. That means this guy. Okay, so now you got two equations, two unknowns. Solve for C1 and C2, and then replace the C's with your answers, and that would be a particular solution. Do we all see it? Yeah, we good. Everyone is okay. I know it went a little bit fast, but do you all see it? Any questions so far, guys? Please let me know so I can back up, tell you what I did. So are we okay with this problem? If you allow me, let me not solve for C1, C2, that takes time, but you see the procedure, so I can show you something else. Are we okay? Yeah? We good? Everyone happy?
Yeah.
Yeah? Okay. So the idea now is as follows. What if, so I'm just going to give you a little taste of what 4.3 is, but we'll finish this Thursday. So let's just go for 10 more minutes and then Thursday. What if you set the auxiliary polynomial equal to 0 and the answer comes up to a complex conjugate? So this is called complex roots. What now? Okay, what now? Well, turns out we have a very nice formula. It's called Euler's formula. So Mr. Euler, many, many moons ago, came up with this magic formula, which says e to the power of I theta is equal to cosine theta plus I sine theta. This is called Euler's formula. Okay, so where do you think Mr. Euler came up with this? Right? So if you don't mind, let me take you to Cal 2, you know, your favorite topic. What? Power series. Remember the power series for e to the x was summation of x to the n over n factorial, n goes from 0 to infinity. So if you would expand this, you would get this power series. And the domain of this power series is what? X is all real numbers. So this is the domain of convergence. In other words, this guy converges for all real numbers. There's absolutely no restriction. Okay, so what if I replace this x with I theta? So that would be sum of I theta to the power of n over n factorial. N goes from 0 to infinity. So this would be 1 plus I theta over 1 factorial. I theta squared over 2 factorial. I theta cubed over 3 factorial. And I theta to the 4 over 4 factorial, and it goes. But keep in mind, I is equal to square root of -1, so I squared is -1, right? That's that imaginary number. So if I simplify this, I get 1 plus I theta over 1 factorial. But check this out. Here, when you square I, you get minus theta squared over 2 factorial. Here, I cubed is what? Is I squared times I, but I squared is -1, so you get negative I. So that would be negative I theta cubed over 3 factorial. I to the 4 is what? Is I squared, which is -1 squared, which is 1. So you get theta over 4 factorial. And it goes, and the sign alternate. So these are real numbers, but these are imaginary. So let's regroup this. Write it as 1 minus theta squared over 2 factorial plus what? Theta to the 4 over 4 factorial, dot, dot, dot. And then let's group these guys. Factor out an I from these fractions, you get what? You get I over 1 factorial minus, excuse me, you get theta over 1 factorial plus what? Theta what? Okay, this doesn't look good. I apologize. Let me just erase that. So I was going to say factor out the I from here. So you get what? Theta over 1 factorial. I factor out the I from here. You get theta cubed over 3 factorial. And guess what the next one is theta to the 5 over 5 factorial. And this goes. But if you still remember your power series, this is exactly the power series for cosine of theta. And this guy is exactly the power series for what? Sine of theta. So that's where Mr. Euler came up with this idea. Do you see it? Or with that magic formula. Correct? So back to our problem. Now what? Well, what happens is the following. Let me now show you what to do when you have complex numbers, but then I'll show you an example next time. So let's just stop it right about here. So remember the solution is still in this form, correct? But we decided, oh my goodness, what if the solution shows up as a complex roots? Okay, remember the complex roots comes in conjugate pair. Okay, you always have a plus bi and a minus bi, rain or shine. So what do we have? Well, we have two complex roots. I'm going to call them W's. One of them is going to be e to the power of a plus bi x. The other one is going to be a minus bix. Is that right? But I'm going to what? Remove the parentheses at the exponent. So this is going to be ax plus what? bxi, which I'm going to split this and write it as e to the ax times e to the what? bxi. Similarly, I'm going to have e to the ax minus bxi because there is a minus. Then I'm going to split this and write it as e to the ax times e to the minus bxi. But then I'm going to use the identity Euler's formula and replace these what? E to the I times something with this formula. Correct? So W1 is going to be e to the ax times cosine of bx plus I sine of bx. That will be this guy. The other guy is going to be W2 is equal to e to the ax times what? Cosine of what? Negative bx plus I sine of negative bx. And that came from here. Do you see it? But wait a minute. Cosine of negative theta is the same as cosine of theta. Sine of negative theta is minus sine of theta. These are identities from trigonometry. And that's due to the fact cosine is even function, sine is odd function. So what are you saying? I'm saying W1 is e to the ax times cosine of what? Bx plus I sine of bx. But W2 is e to the ax. This guy is the same as cosine of bx positive, and this guy is minus I sine of bx. So what are these? These are two complex solutions of our ordinary differential equation, correct? Mayday, mayday, they cannot be the final answers. Why not? Because they are not real solutions, they are complex. What does that mean? Remember, our differential equation was based on a real function. Since the differential equation was based on real function, I cannot have complex solutions for a differential equation where the functions are real. So somehow I got to get rid of these i's. How? I'm going to take linear combination of these solutions, which is going to be solution themselves as well. So the first item would be what? Take, let's say, what? Half of W1 plus W2. So what am I doing? I'm taking linear combination of what? These complex solutions. So I'm going to say C1W1 plus C2W2. I happen to choose the C's as what? As being 1/2 each. And you will see in a minute, why did we choose 1/2 for? Why did we choose 1/2? Can you tell? This would be what? Why is it? Why is it we chose 1/2? Does anyone see why? Because when you add these two equations, let's call this equation 1 and 2, what do we get? Oh, sorry, these equations. What do we get when we add these equations up? What cancels and what stays? Do you all see it? Anyone? Does anyone see what cancels? Sorry? Does anyone see it? If I add these equations, so if I add equation 1 to equation 2, okay, what would
The
I get?
signs cancel?
Yeah.
These guys cancel, so I get two of these. So I get 2e to the ax cosine of bx. That's why I purposely took what? My c1 and c2 to be 1/2. So that way I can get rid of the 2. So there goes what? A real solution with no I in it. There. But wait, I need 2 of these. That's just 1 out of 2. Next time, I'm going to take what? 1 over 2i. Then I'm going to subtract these guys. So in this case, my c's are complex numbers, which is a-okay. There. So my C1 is 1 over 2i. My C2 is negative 1 over 2i. Okay, so when you subtract these guys, you will end up with what? You know, subtract these guys, the cosines cancel. But if you subtract this from this, so that would be what? I sine of bx minus I sine of bx, you get 2i sine of bx. And that's why we have what? What is it called? The scalar as what? 2i. So these guys would cancel. Don't forget we still have a to the x. So lo and behold, the second fundamental solution is e to the ax sine of bx. And these are as real as they get. There is absolutely no evidence of I. Final answer, we get what? Fundamental solutions, e to the ax cosine of bx, and e to the ax what? Sine of bx. The final answer is linear combination of these guys. C1 e to the ax cosine of bx, C2 e to the power of ax, sine of bx. Remember where a and b is coming from. They are coming from the complex roots. This, ladies and gentlemen, is my final answer. Do you see it? So I know I said let's go home. Can I just at least show you one simple problem like this? Okay. 2 minutes. What is the auxiliary polynomial? R squared plus 1 equals 0. So if you solve for r squared equals -1. So that means r is equal to plus or minus I, because the square root of -1 is I. Correct? This is the same as r is equal to 0 plus or minus 1i. Why did I do that for? To show you my a is 0, my b is 1. And this is how my fundamental solutions should look like. So the fundamental solution is e to the 0x cosine of 1x and e to the 0x sine of 1x, you know, sine of bx. So the answer is e to the 0 is 1 cosine of x sine of x. Those are my fundamental real solutions. So the final answer is C1 cosine of x, C2 sine of x. Final answer. The moral of the story is what? If the roots are complex, you can bet your money you're going to have sine and cosine in your answer. That's the takeaway from complex roots. If the roots are complex, the solutions will have sine and cosine in it. And that would be a topic when we talk about harmonic motions, you know, the type of motions which has oscillation in it. And the solutions to that kind of differential equation has sine and cosine in it. Those are called harmonic motion, which is the topic of section 4.9. Very good. Any questions? So we shall continue this on Thursday. Yes? So I was going to post a fake quiz, 2 pages, one of them like, what's your name? The other one like, what's the date today? Just to see if you guys can scan those pages, form a single file, convert the pages to PDF and upload it on Blackboard. This is just a test to see if you guys can do this. So because a week from this Thursday we have a test, so that way we all know how to upload our solutions as a single file in PDF format on Blackboard. So I'm going to post that tomorrow. I'll inform you about it. Please, you know, answer the questions and scan it and PDF it and form a single file. So don't send me like 1 page at a time, multiple pages in a single file. Let me see if you guys can do it so that way I know we are ready to do this on the day of the test. With that said, folks, I will wish you all have a good night. Take care of yourself and I will see you Thursday. Take care. If you have any question, I'll stick around. Good night, guys. Have a good night.